Hello everyone, my name is Roy Jafari, and in this video we are going to learn how we can predict using artificial neural network, specifically using MLP, multi-layered perceptron. Before we get into this video and look at the codes, I want to ask you to make sure that you have watched two of my previous videos. The first one I want to make sure that you have watched is the video I just recently created. That one was about random state. Random state is a property of any predictive modeling algorithm that uses randomization as a part of the algorithm. And I have shown what that random state is and how it is beneficial for a developer to work with it. So that's the first video I want to make sure that you have watched, or at least you are comfortable with property of random state. The second video I would have liked for you to have watched is prediction with linear regression. I have created a video that I predicted the same data set using linear regression. Specifically in this video, we're going to sort of build off of that video. But again, if you feel comfortable with regression and the basic fundamentals of prediction evaluation, such as train and test set, you're welcome to just continue watching. So without further ado, let's get into this and learn how we can predict using MLP or artificial neural network. Let's get to it. So here we are. Of course, as always, the first thing we do, we import the module we are going to be using. This part of the code is from the video that I showed how we could do the same prediction task using linear regression. So if you haven't watched that video, like I said, go ahead and watch that before continuing. But if you feel comfortable with linear regression and the train test dichotomy of validating prediction model, you can just continue watching. But we're just gonna run this and sort of see that linear regression did a much better job than two basic methods of prediction that were random and just putting mean for prediction. And then also look at the metrics, that we can see in the metrics too that linear regression is doing much better than the other two basic methods. So now we're going to turn our attention to MLP. During this video, we're going to have basically two MLP that we're going to be looking at its performance. The first MLP is sort of done in a blind way. We just accept most of the default parameters of the MLP algorithm and just put something based on our experience, based on my experience basically, for the MLP, and just give it a run and see if that is good enough to beat linear regression. And then we take the time to tune the algorithm and see if that's going to change the performance of the algorithm. And since MLP is a flexible and complex algorithm, tuning the algorithm before using it or before final usage is very important, and that's going to be shown in this video. So let's sort of do the MLP in the sort of the blind way. We have just set 5 for hidden size and then maximum iteration 2000. And let's just go ahead and give it a try and see how well this prediction is gonna happen for us. So once we do this, we can clearly see the MLP, which took longer. I mean, you saw that it took a few seconds for this to run. Then linear regression is not actually doing as well as linear regression. We can actually see that also in the metrics, RSME, RMSE, MAE, and MAPE. And we can see that even though MLP is not doing as good as linear regression, but it's still beating the naive, mean, and random methods. So now it's obvious for us, we have to take the time to tune MLP. For tuning any algorithm and tuning MLP, there are so many different parameters that could be tuned. I mean, specifically for MLP, there are so many different things that you could be tuning. But if you have to tune an algorithm you have to sort of change the way we did experimentation. An algorithm such as linear regression that does not need tuning, you can use simply the dichotomy of train, test, validation. But the moment you start needing tuning, you have to change your experimentation a little bit. And this image shows us the experimentation that we did for linear regression that didn't need tuning. We basically split the data into two segments, train set and test set. But now that we need tuning, we cannot tune our algorithm using the test set. We cannot use the train set to predict or to train our algorithm and then see if we can improve it or find the best parameters using the test set. That's just incorrect, because you would be basically overfitting your algorithm to the test set, and then basically test set would not be a good evaluation ground basically for your algorithm. So to avoid that overfitting problem, we have to do something about it. And the way we go about this, and everyone goes about this, is by creating something similar to test set, but it's not really test set. We call it validation set, or I call it tuning set. Basically, validation set is a small part of the training set that it's not the test set, right? So we use this part to sort of evaluate the algorithm, but not as a final evaluation. It's sort of for the evaluation to see which combination of the tuning parameters of the algorithm will lead to the best possible performance of the algorithm. So that's what we need to do first whenever an algorithm needs tuning. So here we basically split the X train and Y train further. The test set doesn't need any change, so we just keep it there. We split X train and Y train. And once we do that, basically we have 4 more chunks. We have X train S, X tune, Y train S, and Y tune. And these are those 4 chunks, and you can also see their shapes here. Basically, we are going to use 804 rows in our data for actual training and 201 rows in our data for tuning. And then I think around 300 or something for testing. One of the things that we have to do every time we do tune an algorithm, specifically those ones that are random based, we have to have more than 1 repetition, because these algorithms are random. If you have 1 repetition, 1 time of the algorithm based on each of these combination of tuning parameters, that might not be enough. So here I have 5 repetition. You can do more repetition. The more repetition you have, of course, the disadvantage is you're going to endure more computation time and computation cost. But perhaps if you have more repetition, your tuning outcome is going to be of more quality, meaning you will have the tuning will lead to a good solution more often, basically. So I suggest that maybe you use 7, 8, 10. For the purpose of this video, to keep it short and sweet, I have put 5. But I think for this video, 5 is enough. But maybe you want to change this number, 7, 8, 10. It might take a little bit longer to do this, these codes for you. But it's good to practice it for at least for this one time that you're going through this code with me. But I have done something. I have pulled this part of the code out, and by just putting a number in front of number of repetition here, you don't have to do anything. The number of repetition will be fixed throughout this code that you can access. So number of repetition is 5. Let's go around and create this, and then I have created a tune df, which is basically a placeholder to keep the performance of my algorithm based on different possible tuning parameters in this placeholder. So every time I, for example, run my algorithm based on identity and BFGS activation and solver, in the first repetition, RMSE comes a number. I just save it here, and then at the end I can come back and basically analyze this table when it's filled, right? So that's what we're going to do. Here I have created 3 nested loops that basically changes these tuning parameters, the activation and solver. That's what we just started here with these 2 tuning parameters, and then see the performance of the algorithm based on the tuning set, and sort of record that performance here. You can see we are using X train S and Y train S, and then once we have a fitted algorithm or trained algorithm, we use that trained algorithm to predict for X tune, which is a prediction for Y tune, and we use that prediction to calculate the RSME, and then we save that RSME in our placeholder. And we once this is run, let me go ahead and start running this. We can come back and look at the failed version of this placeholder to see. Here you will have some warning. These are not errors, these are warning. Some of the combinations of activation and solver don't like each other, and leads to the case that you will have non-value as your prediction. And basically this is part of the tuning, that you would want to figure out that some of these don't go well with each other. So you sort of figure that out as well while you're at tuning it. So once this is run, which should be any second now, we will be able to look at the failed version of this algorithm, this table, and then it can help us figure out what tuning parameter is going to be best in this case. All right, so this is finally done. Now we can go ahead and take a look at the failed version of this placeholder, which has all the performances of these combinations. I've also gone ahead and also included the mean and the minimum of all of the repetitions for these combinations of activation and solve. So once we run this, we will see that the identity SGD gets to perfect prediction, which raises a question. And if you sort of get to the bottom of it, you will understand that these warnings were creating for these, and when this combination is used, the algorithm return null value as prediction. So these are not what you actually need, right? So the best one, there is sort of a tie between ReLU LBFGS and identity LBFGS. Both are having equally good mean, but the tiebreaker is the minimum value, which shows that this combination of tuning parameter has the potential to reach to better possible prediction. So actually in the first few steps for your tuning journey, you want to prioritize the minimum value over the mean, as I have sorted this as mean, because I want to sort of give the algorithm a tuning that has the potential to reach to a better possible prediction. If you look at this combination of identity and LBFGS, you will see that the prediction is almost always the same. So that's why we choose ReLU and LBFGS for these 2 parameters. So after we have this, now time comes for tuning the hidden layer sizes, right? Tuning the hidden layer sizes is a little bit different, because you might have hidden structure with 1 layer or 2 layer or 3 layers. So here I have done the code for experimenting with all the possible 1 layer from that layer having 1 neuron to 15 neurons, and all the possible 2-layered hidden layers for MLP network, where each of the layer could have up to 10 neurons. So these are all of the possible networks I want to do the experimentation with. So this line of code basically created all of those possibilities. Now I have the list of the possibilities. Here I want to do the experimentation. So now I put the activation as ReLU and LBFGS as the solver. I will eventually also tune for max iteration 2000, but let's just keep it 2000 for now. It's a good number for now. We don't need to change that. We will tune it eventually. So we can just hit the run button again. So we hit the run button here, and here I have done something different. Here you can see that I'm printing every time my experimentation for each of these network structure is done. I print a network structure to sort of give me a clue how much my code has been able to process these running, right? So I have some sort of idea where my code is, so I know probably when this is gonna finish. So this is gonna take a while. I'm gonna stop talking, and once it's done, I'm gonna start, going over the rest of this code together. Alright, so after around 5 minutes, this code was done, and we experimented 5 times based on all of the possible network structure that we had come up with. So let's go ahead and see which network structure is giving us the best, the minimum, and the best mean here. So for the network structure, not only we want a good mean, but also we want a good minimum. So let me go ahead and also sort this based on the mean as well, because it's very important for a network structure that is capable of giving us a good mean. So let me see what is the difference there. So based on the mean, we have 10 and 7, and we also have 10 with slightly better possible 15, and then for the minimum, which is 12, around 1300 as well, which reached by this one. So by looking at these two, I think the best actually is to go with 10, right? The reason I'm doing this is that 10 is not as bad, it's not as good as 10 and 7, but it's certainly better than 8 and 2 and 3 and 6 based on the mean. And the minimum here for the network structure is not that significant, because the network structure, you want to make sure that you have a good stability of reaching a good performance. And the reason I'm choosing 10 over 10 and 7 is because 10 has significantly less number of neurons and layers, and leads to faster computation. And perhaps if I had a better computing power, or I had more time, not a video, I could have chosen 10 and 7. But I here go with 10 because of the computational concerns here. Alright, much better. Do I not look better? I saw that I needed to turn on my lights here so you can see me better. Alright, so we go with 10. So now every time we want to do more tuning and the final tune, altitude, tune, MLP, we use 10. Next we want to tune for learning rate and learning rate initialization, right? So These are learning rate method, it can be constant, inverse scaling, and adaptive. And these are the initialization rates. So we experiment with all the possible combination of these with what we have already learned from our experimentation here. So we chose 10 here and 2000. We chose ReLU here, LBFGS, and these are our new experimentation. And like I said, we will eventually tune for max iteration. So let's create our TuneDF here and do our experimentation. Alright, this part of code is also finally over. So now we can look at the result of the experiments. And we can see that based on the best performance, the inverse scaling and the rate 0.01, and based on the mean, I believe the constant 0.005 led to the best performance. So here I think going with either would be okay, but I'm gonna sort of like risk and go with this one because it has more potential to get to a better prediction here. So I'm gonna choose inverse scaling and 0.01. So here I will choose inverse scaling and 0.01. And then finally, we reach at the point we want to shuffle for the maximum iteration. And for shuffle, the shuffle is basically a Boolean, whether we shuffle the train set before each iteration. Do we like put it into the algorithm with the same order as it is in the data, or we shuffle it every time? So we create a TuneDF. And now we do the experimentation. I forgot to change this to 10 as it was what we found. So let's go ahead and run this. As this is running, I forgot to mention that we have, the 2000 was what we've been experimenting with. So I have gone over and under the 2000 and given two options to see doing max iteration more or less is going to help us or not, right? So that's what we've done here. So let's go back, see if our code is done here. So it has reached to 2000. I believe that's it. Yes. So now we can look at the results, and the results tell us that if we did based on the mean, if we did 2000 false, and based on the minimum, if we did 500 and false, it would reach a better solution for us. So here again, I think either of them are okay to choose, because we will see that at the end we will also have a tuning for the random state. So let's go ahead and go with 2000 and false. So we will go with 2000 false. This was 10. This was ReLU LFGS. This was inverse scaling. Let me grab it from here. So it was inverse scaling, and then was 0.01 shuffle false, and finally we are going to tune for the last parameter alpha. So let's go ahead and do this here as well, and I think that's the alright, this is done. So we can look at the outcome. We see that the alpha of 0.00005 reaches the mean, the lowest mean, and then and a little bit lower reaches the minimum. So let's this time go with the minimum and choose this one. And let me put that here. This is our alpha, or let me just copy it from here actually. So copy all of this. We also have the shuffle here. Then finally we have random state. So random state, as we talked about that in the previous video, the video that I recently shared, is not parameters of the algorithm or MLP, but it is sort of like a parameter that Python programming or this module has given us to sort of like give an identity to the randomization that this algorithm is initialized with. So we don't want to sort of like get stuck with a bad randomization, with bad luck, and sort of like just leave what happens to fate. So we want to use the tuning set we already have to see which randomization actually gave us something, a tune algorithm that is sort of like good, and use that one instead of just leaving it to fate. So let's sort of tune for randomness. So that's what we are doing here. We're just going to, let's see what I've done here. Oh, I have, let me see what was the best font. So this was what I wanted to do. All right, so here we go. So we are going to run 9 different ones, and here we go, tune the F. We see that the random state 2 reaches the best prediction for the tuning set. So now here I can choose the random state 2 here, and the rest of those tuning that we had done. So we go ahead and do this, and now I train by X train and Y train, and then this time instead of doing based on X tune, I do X test. And now we can see if tuning MLP is going to have any positive value as far as its performance. So let's go ahead and do it. So here we see, of course, MLP tune is doing better than MLP non-tune, as we can see here. But for us to see the difference, it's very hard to see with our eyes to see if there is meaningful difference here. So let's go ahead and calculate the metrics. And when we do calculate the metric, we do see improvement based on RMSE, based on MAE, and based on MAPE. So we can see that the tune MLP did a better job than linear regression. But pay close attention here. The simplicity and easiness of linear regression giving us a good prediction that after such lengthy tuning process, we were able to only beat, just by a little bit, beat the performance of linear regression. So we have to put it into perspective. We are doing better with MLP tune, but we have to also pay attention to the computational cost. And that's also a very important factor when you choose an algorithm. Alright, in this video, we did predict using MLP. We basically predicted the car prices using MLP. We compared it with linear regression, and also we saw that if we tune MLP algorithm is going to have meaningful impact as far as how successful the algorithm can be. But we also saw that linear regression might not be as good as tuned MLP, but the amount of time we spent on creating linear regression and also the computational cost that went into it was much lower than MLP tune. So that's also something